ናችሁ የተከበራችሁ የኢትዮ ዩኒቨርሲቲ ኤግዚት ኤግዛም ሶሉሽን ሀብ ዩቲዩብ ቻናል ቤተሰቦች እኔ መምህር ጌታሁን ሶርሳ ነኝ። በዚህ ዩቲዩብ ቻናል የተለያዩ የኤግዚት ኤግዛም ጥያቄዎችን በዋናነት ለሜካኒካል ምህንድስና ተማሪዎች የሚሆን ኤግዚት ኤግዛም ጥያቄዎችን እየሰራው ማቅረብ ይታወቃል። ይህ ቪዲዮ ቀደም ብዬ የስትሬንግዝ ኦፍ ማቴሪያል ጥያቄዎችን ከአንደኛ እስከ 8ኛ ያሉ ጥያቄዎችን ሰርቼ አፕሎድ አድርጌያለሁኝ። በዛ ቪዲዮ የተለያዩ ኮሜንቶችን ተቀብያለሁኝ። አሁን ደግሞ የዚህ ቪዲዮ ቀጣይ ፓርት 2 በዚህ ቪዲዮ ሰርቼላችኋለሁኝ። ሁላችሁም ለዚህ ቻናል አዲስ ከሆናችሁ ቻናሉን ሰብስክራይብ እንድታደርጉ፣ ቪዲዮዎቹን ላይክ ሼር እንድታደርጉና በቪዲዮዎቹ ላይ ኮሜንት እንድትጽፉ እላለሁኝ። እንዲሰራላችሁ የምትፈልጉትን ጥያቄዎችን ኦር ኮርሶችን በኮሜንት ቦክስ ላይ በማስቀመጥ ጥያቄዎቹን እኔ እየሰራው ለእናንተ እንዳቀርብ እንድታደርጉ እላለሁኝ። ከዚህ በመቀጠል ቀጥታ ወደ ጥያቄዎች እሄዳለሁኝ።
then maybe ጥያቄው የተለያዩ የማቴማቲካል አናሊሲስ የሚጠይቅ ስለሆነ እናንተም ዳውንሎድ አድርጋችሁ ለማየትም በጣም ረጅም ከሆነ ከባድ ሊሆን ስለሚችል በተቻለ መጠን አጠር አድርጌ ቪዲዮዎቹን ለእናንተ አቀርባለሁ አደርሳችኋለሁ። question number 9, the maximum principal stress for the state of stress shown in this figure, or the figure here, is A, 1 times stress, B, 2 times stress, C, 3 times stress, and D, 1.5 times stress. So here we can analyze this by using the concept of the maximum stress on the, or maximum principal stress on the parts. So here we have given this sketch or this figure, and we are asked to calculate the maximum stress. So here we have given the stress along x and y direction, which is equal stress along x and y is equal. Yeah, we have equal stress along x and y, and we have shear stress also given. We have shear stress which is also given, and which is equal as shear stress along xy, which is also the individual stress. Therefore, we are asked to analyze the maximum principal stress, the maximum principal stress, which is unknown. So let us solve this. We can solve this maximum principal stress by using the formula, the principal or the stress along x, or the summation of stress along x and y over 2 plus square root of stress along x minus stress along y over 2 the whole square plus shear stress along xy the whole square. So by using this formula we can calculate, or we can analyze the maximum principal stress for the given part. So this is the general formula, and here we have given the stress along x and the stress along y, which is equal, and here we have given also the shear stress along xy is also equal with this part. So these all are given, and when we substitute the values, the maximum principal stress, which is equal with stress plus stress over 2 plus under radical. Here we have equal value here. Stress along x and y are equal, and when we subtract this equal part from each other, we get this 0 value, 0 square, plus this part is given as stress, so stress square. Here when we take this from out of radical, then it becomes here 2 stress over 2 plus stress, and when we cancel this part, this maximum stress or maximum principal stress for that part or for this part is 2 times individual stress. So the maximum principal stress on this part or on this body is equal with 2 times individual stress. So the correct answer with this value is at choice B, this choice B, which is correct answer for this question. This choice B is the correct answer. Therefore, the maximum principal stress for the state of the stress as shown in this figure is, which is equal with 2 times the individual stress. Okay, let's go to the next question. Question number 10. Maximum shear stress in the Mohr circle is A. It's equal to radius of Mohr's circle. B. It's greater than the radius of Mohr's circle. C. It's less than radius of Mohr's circle. And D. None of the above. Therefore, let's see the explanation. Here we are asked to calculate the maximum shear stress, or we are asked to decide what the maximum shear stress on the Mohr circle seems like. In this, here we have the Mohr circle like this, the Mohr circle like this, and from the Mohr circle, for a plane stress, the maximum shear stress, it occurs at the points where the circle intersects the horizontal axis. Here we have horizontal axis, and when the circle rotates, and there is the maximum shear stress occurrence at the point where this circle intersects with the x-axis or the horizontal axis. And the maximum shear stress, tau max, is given by the diameter of the circle. It is usually given by the diameter of the circle, and it is equal with the radius of that circle. Therefore, the correct answer or the correct option with this concept is choice A. The maximum shear stress in the Mohr circle is equal to the radius of the Mohr circle. So the maximum shear stress on the Mohr circle, it is equal with the radius of the Mohr circle. So choice A is correct answer for this option also. For this question, this choice A, the maximum shear stress in the Mohr circle is equal to the radius of Mohr circle. The next question, question number 11. A massless beam has a loading pattern as shown in this figure. The beam is of rectangular cross section with a width of 30 mm and height of 100 mm. So here we have given this type of figure with the values, the length from A to B, which is 2000 mm, the length from B to C, which is 2000 mm also, and the uniformly distributed load from point B to point C is 3000 Newton per meter. And here in this part, in point C there is hinged part, and on point A there is fixed part. So we are asked to calculate the point where the maximum bending moment occurs. So the maximum bending moment occurs at A, location B, 2675 mm to the right of A, C, 2500 mm to the right of A, D, 3225 mm to the right of A. So at which point is the maximum bending moment occur? This is a solution. So here we have this type of figure and this type of beam with uniformly distributed load, and here we have reaction force. Here we have reaction force at point C and reaction force at point A, and we have to take the summation of reaction force, which is equal to 0, to analyze the reaction forces at each point. So here we have point A and point C, and the reaction force along point A or at point A plus reaction force at point C, which is equal with, here we have 3000 Newton per meter, and the distance from this the distance for here we have 2 meter. Here we have 2 meter. The distance from this to this is 2 meter, and here the load is distributed 3000 Newton per meter. That means we per 2 meter, it becomes 2 times 3000 Newton per meter, and we have a reaction force along A, or reaction force RA plus RC, which is equal with 2 times 3000 Newton, which is, here we have 6000 Newton. And the maximum bending stress on the beam is given us here. We can calculate the maximum bending stress by using this force, and here the maximum bending stress, which is calculated as maximum bending moment over Z, which is section modulus, and this is the maximum bending moment. And usually this Z is calculated by using I over Y for rectangular section. So in this we have given that the load is 3000 Newton per meter. The summation of reaction force along, or the reaction force at A and reaction force at C, which is equal with 6000 Newton. And let's take this as equation 1. And here the moment about point A, when we take the moment at point A, the MA, which is equal to 0, or the summation of moment at point A, which is equal to 0. And here we have, in this here, where the forces are distributed from this point to this point. The points are distributed. Here there is uniformly distributed load here in this point. So for this, the distance from this to this is 2, and the distance from this to this is also 2. So for uniformly distributed load, the moment is occurred at L over 2. To calculate the moment from point A to this, that is 3, or when we sum up this, the moment occurs at L over 2. And here we have 6000 Newton times, here from this to this is 2, and from this the moment is occurred at the center also, here full of this, that means 2 meter, and half of this, which is 1 meter. When we sum up this, there is 3 meter. So 6000 Newton times 3 meter minus RC means from this to this, which is 2 meter plus 2 meter, which is 4 meter, and which is equal with 0. And when we arrange these values, this part by 4, and this part by 4, 1500, and times 3, which is 4500 newtons. And when we substitute this value on the equation 1, on this equation, here we have RA plus RC, which is 6000. When we replace the value of RC as 4500 Newton, and RA becomes RA, which is equal to 6000 Newton minus 4500 Newton, it becomes 1500 Newton. So this is the value of RA. So RA becomes 1400. RA equal with 1500 Newton.
Therefore, to calculate the point at which the maximum bending moment occurs, we have to take any section X from point A. We can take any section, and here if we have this type of the sketch that we have given like this, here we have point A, point B, and point C, and here the load is 3000 Newton per meter square, and we have distances given from B to C, which is 2 meter, and from A to B, which is 2 meter also. And to analyze the values, or to calculate the value, we will have to take the distance X from point A, here distance X, and we can simply analyze this value. So this is the distance from A to the point at which the maximum bending moment occurs. So we have to calculate, or we have to analyze for this X value,
And to analyze this here we have shear force, which is 1500 minus 3000 into x minus 2. We have to equate this shear force with 0, and we have 1500 Newton minus 3000 into x minus 2 meter, which is equal with 0. And when we substitute the values, or when we rearrange the values, here we have 1500 Newton minus 3000 Newton times x plus 6000 Newton, which is equal with 0. And when we take the like terms, here we have 1500 and here we have 6000. When we sum up this, it becomes 7500, which is equal with 3000 Newton x. So when we to calculate for x, we have to divide both parties by 3000. Here we have 3000 and here we have 3000 also. And when this part becomes 0 and this part becomes 0, and the remaining part is 7.5 over 3. Then when we divide this 7.5 by 3, it becomes 2.5 meter. The distance at which the maximum bending moment occurs is at the point 2.5 meter right to A, or 2500 millimeter to the right from A. So when we analyze this, the maximum bending moment occurrence point, it is 2.5 meter right from A, or 2500 millimeter right from A. For this, the given figure, the maximum bending moment occurs at this 2.5 meter right to A, or 2500 millimeter to the right of point A. Question number 12. A steam beam of width is 120 millimeter and height of 750 millimeter is loaded as shown in the figure. Assume the modulus of elasticity for this steel is 200 gigapascal. What the maximum bending moment and maximum deflection of the beam? A 3375 kilonewton times meter and 93.75 millimeter. B 4750 kilonewton times meter and 83.75 millimeter. C 6750 kilonewton times meter and 73.75 millimeter. D 8750 kilonewton times meter and 63.75 millimeter. So let us see the solution. We have B, which is, or the width, which is given as 120 millimeter, height, which is 750 millimeter, modulus of elasticity of the material, which is 200 gigapascal, which is equal with 200 times 10 to the power of 9 Newton per meter square. And we have given uniformly distributed load as 120 kilonewton per meter, which is equal with 120 times 10 to the power of 3 Newton per meter. And these are the given parties, and it is given that the load is uniformly distributed. So we know that for uniformly distributed load, the maximum bending moment occurs at the center, which is usually given by maximum bending moment, which is equal with W L square over 8. Here we have W given as 120 times 15 square, 120 times 15 square over 8, which is in kilonewton per meter. Here W, or the load, is given as kilonewton. And when we calculate this, the maximum bending moment is 3375 kilonewton per meter. From this, the maximum bending moment is 3375 kilonewton per meter. So this is the correct answer.
And next, we are asked to calculate the maximum deflection, and to analyze this, we have to calculate the moment of inertia I, for this cross section. So the general formula to calculate the moment of inertia I is B times H cube over 12, and B, which is given as 120 millimeter, which is equal with 0.12 meter, and this H is given as 750 millimeter, which is 0.75 meter. When we insert these values or substitute these values on the general formula here, 0.12 meter into 0.75 meter, the whole cube over 12, it is equal with 4.22 times 10 to the power of minus 3 meter, the power of 4, or M4. This is the unit for moment of inertia. The maximum deflection is calculated as, or for this cross section, the maximum deflection is calculated as 5 over 384 times WL is the power of 4 over E times I. E is modulus of elasticity and I is the moment of inertia. And when we insert the values, we have given that W, L, E, and I also. So the next step is only substituting the values, and when we substitute the values, it becomes like 5 over 384 times 120 times 10 to the power of 3 Newton into 15 meter. This L is the length of the beam, which is 15 meter, the power of 4 over this E is given as 200 times 10 to the power of 9 Newton per meter square, times this I is calculated as 4.22 times 10 to the power of 3 M4. And the maximum deflection of the beam is equal with 0.09372 meter, and when we multiply this by 1000, it becomes 93.72 millimeter. Therefore, the maximum bending moment and the maximum deflection is approximately 3,375 kilonewton times meter and 93.75 millimeter respectively. And the choice with this answer is choice A. Choice A is correct answer for this question. So the maximum bending moment and maximum deflection of the beam with this given beam is this part. The maximum bending moment is 3,375 kilonewton times meter, and the maximum deflection of this part is 93.75 millimeter. So this is the correct answer. Question number 13. If the shear force diagram for a beam is triangle with a length of the beam as its base, the beam is A, a cantilever with a concentrated load at its free end, B, a cantilever with uniformly distributed load over its whole span, C, simply supported with a concentrated load at its midpoint, D, simply supported with a uniformly distributed load over its whole span. Okay, let's see the explanation here. We have, it is given that the shear force diagram for a beam is triangle with length of the beam as its base. That means here we have the shear force diagram as a triangle, shear force diagram as a triangle. And if the shear force diagram is a triangle, its typical indicates a linearly varying shear force. There is the shear force is varying linearly, and which is associated with a uniformly distributed load over the whole span of the beam. When the load is distributed uniformly at the whole span of the beam, the shear force diagram is, it seems like a triangle. It indicates that a linearly varying shear force on that part. So this condition is more accurately described by option B, a cantilever with a uniformly distributed load over its whole span. So if the shear force diagram for a beam is a triangle with a length of beam as its base, the beam is a cantilever with uniformly distributed load over its whole span. So this is choice B is the correct answer
choice B. This is the correct answer. So number 1-4. A cantilever beam carries a load W uniformly distributed over its entire length. If the same load is placed at the free end of the same cantilever, then the ratio of maximum deflection in the first case to that in the second case will be A 3/8, B 8/3, C 5/8, D 8/5. Let's see the solution. The end deflection of a cantilever carrying uniformly distributed load is usually given by this. The end deflection of a cantilever carrying uniformly distributed load is given by the deflection 1, which is equal with WL³/8 times EI. This W is the load, this uniformly distributed load on the part. L is the length of the cantilever. E is the modulus of elasticity. E is the modulus of elasticity, and I is the moment of inertia. And in the second case, the end deflection of a cantilever carrying a concentrated load as the free end is given by WL³/3 times E times I, where W is the uniformly distributed load, L is the length of the cantilever, I is the moment of inertia, and E is the modulus of elasticity of a material. Therefore, when it is given that if the same load is placed as the free end of the same cantilever, then the ratio of the maximum deflection in the first case to that of the second case. So we are asked to calculate the ratio of the maximum deflection. Therefore, we are asked to analyze this deflection 1 by deflection 2, or the ratio of the deflection 1 to deflection 2. Therefore, the ratio of the maximum deflection in the first case to that in the second case will be W, or it will be here this deflection 1 over deflection 2, deflection 1 over deflection 2. So deflection 1 is WL³/8 EI, WL³/8 EI over WL³/3 EI. And when we rearrange this, WL³/8 EI times 3 EI over WL³. Therefore, here we have EI here, it will be cancelled, and here there is WL³, it is cancelled also, and the remaining part is 3/8. Therefore, the correct answer for this question is choice A. Therefore, a cantilever beam which carries a load W uniformly distributed over its entire length, and if the load is placed as the free end of the same cantilever, then the ratio of maximum deflection in the first case to the second case is 3/8. 3/8. This A is the correct answer. Question number 15. Match list 1 with list 2 and select the correct answer using the code given below the lists. Here we have list 1, toughness, endurance strength, resistance to abrasion, deflection in a beam. And list 2, we have moment area method, hardness, energy absorbed before fracture in a tension test, and fatigue loading. So here we are asked simply to match the term with its meaning. Here we have codes. A, B, C, D. So which one is matched correctly, or which one explains the correct meaning of each term? At A, here 4, 3, 1, 2. B, 3, B, 4, 3, 2, 1. C, 3, 4, 2, 1. And D, 3, 4, 1, 2. So we have for code A, for
for list 1 we have codes here, and for list 2 we have codes here, and which pair exactly explains the meaning of each term at point A. Therefore, to analyze the correct matching, we have to know the meaning of each part. So here, when we say toughness, it is correctly matched with point 3 or number 3. Its toughness means energy absorbed before fracture in a tension test. Its toughness is energy absorbed before fracture in a tension test. And endurance strength means it is fatigue loading. Endurance strength means it is fatigue loading. This B is matched with 4. And resistance to abrasion is hardness. It is hardness. So this resistance to abrasion is correctly matched with hardness. And deflection in a beam is moment area method. So this is correctly matched with moment area method number 1. Therefore, the correct answer with this matching is A3, B4, C2, and D1. The pair with this is at point C. So here at point C, A means it is toughness. Toughness is directly related with what? 3, energy absorbed before fracture. And this B, which is endurance strength, which is correctly matched with 4, fatigue loading. And C, resistance to abrasion, which is hardness. It is hardness here. And D, deflection in a beam is moment area method. So the correct answer for this question is choice C.
ለዚህ ቻናል አዲስ ከሆናችሁ ቻናሉን ሰብስክራይብ እንድታደርጉ፣ ቪዲዮዎቹን ላይክ ሼር እንድታደርጉና በቪዲዮዎቹ ላይ ኮሜንት እንድትጽፉ እላለሁኝ። እንዲሰራላችሁ የምትፈልጉትን ጥያቄዎችን ኦር ኮርሶችን በኮሜንት ቦክስ ላይ በማስቀመጥ ጥያቄዎቹን እኔ እየሰራው ለእናንተ እንዳቀርብ እንድታደርጉ እላለሁኝ።